On Christmas Eve of 2024, while most of the planet was wrapping presents and setting out cookies, a machine the size of a small car was diving directly into the atmosphere of a star, not photographing it from a safe distance, not orbiting nearby, flying straight into it, skimming through material so hot it would vaporize steel in seconds, at a speed no human-made object had ever reached before or since. And then, for 36 hours, NASA heard nothing back. No signal, no confirmation the spacecraft had survived. Just silence, while a team of engineers who had spent the better part of a decade building this thing sat and waited to find out if their machine and their life's work still existed. Here's the part that should genuinely stop you. This wasn't a fluke or an accident. NASA planned this. They designed a spacecraft specifically to survive inside a star's atmosphere, on purpose. And they've now done it successfully more than 20 times. By the end of this video, you'll understand exactly how you build something that can survive that, why it took 6 years just to get there, and what this machine found inside the sun that's already rewriting how we understand space weather and how it threatens Earth. Let's start with why the corona, the sun's outer atmosphere, is arguably the most dangerous environment humanity has ever tried to study up close. You'd think the closer you get to the surface of the sun, the hotter things get, in a simple, predictable way. And that's true, until you reach the corona, and then something bizarre happens. The sun's visible surface, the photosphere, sits at around 10,000 degrees Fahrenheit. But the corona, the wispy outer atmosphere that extends millions of miles beyond that surface, somehow reaches temperatures of over 1,000,000 degrees. It's hundreds of times hotter than the surface directly beneath it, and nobody has ever had a complete explanation for why. It's a bit like walking away from a bonfire and discovering the air 10 feet away is hotter than the flames themselves. That contradiction has been sitting unsolved in solar physics for more than 50 years, and it's one of the central mysteries this mission was built to crack. The corona is also where the solar wind is born, a constant stream of charged particles blasting outward from the sun in every direction, racing across the solar system at hundreds of miles per second. When that wind slams into Earth's magnetic field, it can trigger the northern lights, sure, but it can also knock out satellites, disrupt GPS systems, and in extreme cases, threaten power grids across entire continents. Understanding exactly how and where that wind gets accelerated isn't just an academic curiosity. It's the key to predicting space weather with the same kind of advance warning we get for a hurricane. To actually answer these questions, scientists realized decades ago that you couldn't just observe the corona from Earth or even from orbit nearby. You had to go inside it. And that idea sat on the shelf for over 60 years because nobody had the technology to build something that could survive the trip. The mission that finally did it carries the name of the man who predicted the problem in the first place. In 1958, a young astrophysicist named Eugene Parker published a theory that seemed almost absurd to his peers at the time. He proposed that the sun wasn't just quietly radiating heat and light into space, but was constantly ejecting a stream of charged particles in all directions, what we now call the solar wind. Most of the scientific establishment dismissed the idea. One journal reviewer reportedly rejected his paper outright. But when NASA's Mariner 2 spacecraft flew past Venus in 1962, it directly measured exactly the kind of particle stream Parker had predicted. He'd been right. In the field of heliophysics, the study of the sun's influence across the solar system was never the same again. Decades later, when NASA finally built a spacecraft designed to fly directly into the corona, they named it after him, Parker's Solar Probe. It's the first NASA mission ever named after a living scientist, and Eugene Parker himself was there in 2018 to watch it launch, at the age of 91. Now here's where the story becomes an engineering problem. Because knowing you want to fly into the sun's atmosphere and actually building something that survives it are two very different challenges. The single biggest obstacle wasn't heat in the way most people imagine it, like an oven slowly cooking the spacecraft. It was intensity. At its closest approach, Parker's Solar Probe's heat shield faces temperatures of around 2,500 degrees Fahrenheit, hot enough to melt steel. The solution the engineers landed on is a shield called the Thermal Protection System, a carbon composite disc about 8 feet across and only 4.5 inches thick, made primarily of carbon foam, sandwiched between two carbon plates. Carbon was the key. Unlike most materials, carbon composites don't just resist heat. They actively resist conducting it, meaning the front face of the shield can be glowing at thousands of degrees, while, just inches behind it, the spacecraft's instruments sit comfortably at around room temperature, roughly 85 degrees Fahrenheit. Think about that contrast for a second. 2,500 degrees on one side of a shield less than 5 inches thick, and room temperature on the other. That's the entire trick that made this mission physically possible, and it took engineers years of testing to get the carbon layup and coating exactly right, because even tiny imperfections could create weak points that would fail catastrophically the moment the spacecraft got close. But surviving the heat was only half the challenge. The other half was actually getting there. And this is where the 6-year approach comes in, because you cannot simply point a spacecraft at the sun and fly toward it. It's counterintuitive, but reaching the sun from Earth actually requires an enormous amount of energy, because Earth itself is moving sideways around the sun at about 18.5 miles per second. Any spacecraft launched from Earth inherits that sideways motion, and canceling it out to fall inward toward the sun takes far more fuel than any rocket could practically carry. So instead, engineers used a technique called gravity assist, and Parker's solar probe used it more aggressively than almost any mission before it. The spacecraft was sent on a series of 7 separate flybys of Venus, spaced out over nearly 6 years, using the planet's gravity each time to steal a small amount of its orbital energy and bend its own path a little closer to the sun. Each Venus flyby shaved down the spacecraft's orbit, tightening the loop, bringing the closest point incrementally nearer to the solar surface with every pass. It's a slow, patient, almost surgical process, borrowing momentum from a planet 7 separate times just to arrive at your real destination. By late 2024, after that 6-year approach and 21 previous close passes through progressively hotter regions of the corona, the spacecraft was finally ready for its record attempt. On December 24, 2024, Parker's solar probe made its closest approach yet, flying within just 3.8 million miles of the sun's surface, about 6.1 million kilometers. To put that in perspective, Earth orbits the sun at an average distance of 93 million miles. Parker was, proportionally, close enough that if the distance from the sun to Earth were the length of a football field, Parker would have been standing about 4 yards from the end zone. At that distance, the spacecraft reached a top speed of 430,000 miles per hour, fast enough to travel from New York to Tokyo in under a minute. No human-made object, before or since, has ever moved that fast. And then, exactly as engineers had planned for, the spacecraft went silent. Because it was flying directly between Earth and the sun during its closest approach, its antenna couldn't maintain contact, and the intense solar interference made any signal essentially impossible to detect anyway. The mission team back at the Johns Hopkins Applied Physics Laboratory in Maryland had no way to know, in real time, whether their spacecraft, the product of a decade of work, had survived. For 36 hours, they simply waited. No updates, no telemetry, nothing. Then, late on December 26th, a faint beacon tone reached the Mission Operations Center. A single, simple signal that meant exactly one thing. The spacecraft was alive, healthy, and operating normally. One team member later described the moment the room erupted, after over a day of tense, quiet waiting, as one of the most emotional moments of the entire mission. So what did the spacecraft actually find once scientists got their hands on the data? The centerpiece discovery involves something called switchbacks, strange zigzag kinks in the sun's magnetic field that Parker had first detected years earlier, much farther from the surface. Nobody knew exactly where they came from or what they meant. But on this closest pass, flying directly through the region where they form, Parker's solar probe finally traced these switchbacks back to their source, small magnetic funnel structures on the visible surface of the sun itself. Scientists now believe these switchback structures act almost like tiny jets, injecting bursts of energy directly into the corona and helping kick the solar wind up to its full speed. It's a piece of a 50-year-old puzzle, finally clicking into place. the mechanism that helps explain how the sun's atmosphere accelerates outward across the entire solar system. The mission also captured the closest, most detailed images ever taken of the corona directly, using an instrument called WISPR, the Wide Field Imager for Solar Probe. Those images revealed the boundary of the corona itself is far from smooth. It's wrinkled, spiked, and uneven, shaped by the same turbulent magnetic activity driving the switchbacks below. And critically, the data helped confirm something scientists had only theorized before, that there are actually two distinct types of slow solar wind, one carrying the same kind of magnetic fluctuations as the fast wind, and one that doesn't, suggesting they're born through entirely different physical processes, even though they end up moving at similar speeds. None of this is just abstract physics. It matters because the solar wind and the violent eruptions that occasionally ride along with it are the direct cause of space weather here on Earth, the kind of event that can overload power transformers, scramble satellite navigation, and threaten astronauts and airline crews flying over the poles. Understanding exactly where and how these particle streams are accelerated is the first real step toward forecasting space weather with the kind of lead time we currently get for hurricanes, rather than the current reality where a solar storm can sometimes give us less than a day of warning before it slams into the planet. Parker Solar Probe wasn't finished after that Christmas Eve flyby, either. It went on to complete 2 more passes at that same record distance on March 22nd and June 19th, 2025, closing out the 24th and final perihelion of its primary mission. But the spacecraft itself is still out there right now, still orbiting, still gathering data, with additional close passes continuing well beyond its original mission timeline, including one in September of 2025, and NASA has indicated the spacecraft could keep flying and returning usable data for years to come, fuel and hardware permitting. What's genuinely remarkable, sitting back and looking at the whole arc of this story, is how much of it traces back to a theory one young scientist proposed in 1958, one that the scientific establishment initially waved off as implausible. It took over 60 years, 7 gravity-assisted flybys of Venus, a heat shield built from carbon that can hold a temperature difference of over 2,000 degrees across 5 inches of material, and 36 hours of total silence on Christmas Day. But in the end, Eugene Parker's prediction wasn't just confirmed. A spacecraft carrying his name flew directly into the region he first theorized, and came back with the answers he spent his career searching for. We've now flown a machine into the atmosphere of a star, and it's still up there, still working, still sending back pieces of a puzzle scientists have been chasing for half a century. And somewhere in the data it's still transmitting, there are almost certainly answers to questions about our sun that we haven't even figured out how to ask yet.